All right, so we've covered a lot of ground today. I'll just do a quick review, and then this little guy right here at the bottom is what I want to focus on. Very important. So we've done the Hellgate turbine project. That was fun. Came up with our solution. File, save. So we've been in a lot of different spaces. We've been with wind. We did the solar thermal payback. So we looked at a solar thermal offsetting a solar electric on a house. Came back with a relatively short, less than 1 year payback time. And now we're doing a little bit of heat transfer. So one thing that I've tried to make clear is that U is thermal conductance, depends on how much of a material you have, and K is thermal conductivity, and that's a material property itself. So let me, again, I want to focus right here. So Q dot equals UA delta theta. So let's just run that with two different scenarios. Q dot equals UA delta, and I'm going to do T, equals K over D A delta T. So let's look at two separate scenarios, and I'm just going to, well, now let's run it this way. So here's A. So we're going to run two different systems side by side. And what I'm going to ask you for is Q dot 1 equals and Q dot 2 equals. The only thing I'm going to change is the D. So A1, A2, and I'm just going to say A1 equals A2. And we'll have delta T1, delta T2, and I'll just say that delta T1 equals delta T2. So the areas are equal, the change in temperatures are equal. This is K1, so the thermal conductivity of material of wall 1, thermal conductivity of wall 2. I'll just say that K1 equals K2. But now I'm just going to say that D, and that's the thickness, this is D1, this is the thickness, this is D2. I'll say that D2 equals 2 times D1. And so let's just look at the, let's just look at and see how that affects the heat flow. Let's see how that affects the heat flow. And so basically what you've got, let's just say you've got like 8-inch studs instead of 4-inch studs in your wall. That's really all it comes down to. So we know that, we can just write them both out. Actually, I think I can squeeze this on the same page. So Q1 1 dot equals K1 D1 A1 delta T1. Q2 dot equals K2 D2 A2 delta T2. Now we know that all the K's, the delta T's, everything are equal. So the easiest way to deal with that is to say Q1 dot equals K. I'm just going to call it K because K1 and K2 are the same. I'll just leave this as D1. A is the same, and delta T is the same. And now Q2 dot equals K, because both K's are the same. And now here's where the difference comes in. 2d2 A delta T. So now let's just solve for that, and we'll say that Q1 dot D1 equals K A delta T. Q2 dot times 2 D, oops, I made a mistake, 1 second. That's, so since we know that D2 is equal to 2D1, that's what I wanted to show there. So Q2 dot equals 2 D1 equals K A delta T. So from that, we can just say that Q1 dot D1 equals Q2 dot 2 D1. And then Q1 dot equals 2 Q2 dot. Pretty simple and pretty straightforward, because we know that, so here's the heat, so Q1 dot is the heat flowing through that wall, Q2 dot is the heat flowing through that wall. So we've obviously shown that heat is flowing twice as fast through the thin wall as it is the thick wall. That's it. So that's so we didn't change the material. We just said that this is the heat transfer coefficient for wood. Probably somewhere on here there's wood. Go all the way down here. Milk, peat, pitch, polystyrene, slate, soot, timber. And there are the numbers. They're all kind of in the same ballpark. And you can see that different woods have different thermal conductivities. So you haven't changed anything. You just made the wall thicker, and it's very straightforward. So I make the wall thicker, I'm going to lose less heat. Okay. Yeah.
Okay.
That's the difference, and that's the difference between, and it's the same way. It's the same thought process in reverse for thinking about R values, because R is just 1 over U. Okay. What's next? All right, so this problem, I think, gave a few people some troubles too. So here's what we're looking at with this guy. Okay, so what we have, again, horizontal axis wind turbine, and it's a 2-bladed design. And the question is, so this rotation, the spin, we'll just call that the spin. If for some reason the head of the turbine were to pitch up and down like that, that would be the pitch. But as the wind velocity changes, so if we look at this from the top, here's the top view. top view. This is the side view. As the wind changes from this direction, now it's over here, and you've got your vane out the back. This direction of rotation is called yaw. So the question asks, why might a two-bladed turbine that is yawing into the wind do so in a jerky manner? Why would it just spin slowly? Why would it shudder or jerk as it doing so? Well, if you remember, let's see if I can find something online. This is the perfect analogy. Give me one quick second. So hopefully you can see this. I'm actually sort of getting chills watching this. So here she goes into the spin, but as you can see, as she tightens up, she spins faster. Right? That's so she comes in, she's got some rotational momentum there, spinning relatively slowly because her leg is stiffened. She brings it in, spins faster, pulls it out, and slows down. So her leg is level, and as she sticks her arms all the way up, this particular event in history happened when I was 6 years old, and so I still have memories.
A jubilant Hamill put in the free skating performance of her career to the delight of her many fans in the crowd.
So back to our problem with the wind turbine. So this view that I'm showing you here is Dorothy Hamill with her arms sticking up in the air. We could also, if we did a front view, let's do a front view of the turbine. There's a point in time where the blades are sticking out like this, right? And so as this thing is yawing, and again, this is our top view, this is our front view. As it's yawing, the blades are going from arms extended to arms above the head. So as that's happening, this yawing rotation is accelerated and arrested as the blades are spinning. So as it's doing this and trying to spin, you can see that that affects the spin rate, and it could cause shuddering and jerking in the mechanism. Okay. While we're on this topic of wind turbine design, I just love going out and looking at some of these things that are, much more elegantly crafted. So here's something where somebody's got a sort of a sail, and all of your turbine action is in here. These guys are just sort of like much smaller. You can imagine this going to any scale you want, but sort of as wind blows through the structure, these little guys spin. This turbine is actually floating. It's got a wing that takes it up. So the higher it goes, the better it works. This guy's sitting there out at sea. And it's obviously spinning about this axis. Gearboxes are at ground level. Kind of wild. This is just a whole set of little antenna just kind of whipping around back and forth. So the energy generation is right down here on the ground, and I'm guessing this is probably some kind of excuse me, some kind of probably not a gearbox at the bottom. It's probably more of a piezoelectric at the bottom. But this is the one I wanted to show you. Kind of cool looking. This guy's going to have the same problems when it rotates, but as you can see, he has these other two counterweights, so that is reduced. And we could go through some mathematics and see what this thing does versus the this front view thing that we looked at a second ago, but,
That's strange.
yeah, I know. I love this one too. So this is just, again, a little piezo. And a piezo is basically how your microphones work in your, microphones and speakers work. As a material is excited electrically, then vibrates mechanically. So this is the same thing in reverse. It's just a big microphone, basically, is all it is. Taking the mechanical energy from the wind and turning it into just, enough electricity to, have some light. Love that thing. So this thing is actually tiny, skinny, really, just tiny. This type of technology is sometimes called energy scavenging. You're sort of putting it somewhere where you otherwise wouldn't think of putting a renewable energy tech. Kind of artsy. $30,000 feet. So this is like, Ben Franklin on steroids, looking to actually even tap the jet stream. And you could imagine these being filled with helium or hydrogen. So, anyway, I love looking at that stuff. All right, well, I think we're right about time, but I think we made a lot of progress today, covered a lot of ground, went over a few sticky problems in the course. I'll be sure to post these so everybody's got a chance